Good morning.
I was like paranoid all night last night. My place is janky as hell. Yeah, stuff on it. Kind of like 2D process and stuff. Some of the real ones big.
The serial killers, unsolved murders. Yeah, so it's a good thing.
I didn't need that. I was like, well, my apartment's old, and I'm pretty sure there's squirrels in the roof. You hear it hanging around, but like, yeah, it's like, oh, that's not me. Oh, okay. Let's see, where's this? Is this?
It's the same Zoom.
Yep. Yeah. Instead use one task. Instead, at least the homework, use one task to find just one task. I'm playing like a muscle screw card and then come back here and muscle screw card.
Howdy, everybody. Welcome.
Oh, yeah.
No, that's not it. All right. There it is. Okay, so I am, let's see, share desktop, sharing. So over here we should be. All right, so I'm going to assume that everybody is here. We only have 11 participants, so I assume some folks are sharing a screen. Welcome, and while I had not figured out this aspect last week of Zoom, but I have brought up the Zoom chat window, so that's available on the toolbar. That's either down at the top or at the bottom of your Zoom screen. And if during the course of the lecture, if you have questions, or if you have just general questions, perhaps about the homework assignments, that sort of stuff, you can go ahead and type them in while we're talking over there on the Zoom chat group. So today we're going to talk about semaphores. I don't anticipate this lecture is going to go the full hour. It's a relatively straightforward concept, but as you do embedded systems work with real-time operating systems and kernels, there are two things that you're going to use most frequently. One, of course, are timers, because so much of what we do is based on time of execution. But the other area where you're going to use a lot and virtually every real-time multitasking application is going to use a semaphore. Now, semaphore, the term actually comes from railroading. If you've ever stood on a railroad track and looked particularly near intersections or where there are double tracks, if you look down where the engineer sees, you'll see these poles that look like what you see there that are called semaphores. And the concept of a semaphore is that if the semaphore is in that down position that shows an alternate red light to the engineer so they can see it in the evenings, then that means that the track ahead is not clear, that the engineer cannot proceed on that track. If the semaphore is up and the little green light is showing, then that says that the track ahead is clear and the engineer can run at full speed ahead. This has been this way for centuries in railroading. And it's basically, a semaphore is a locking and synchronization mechanism. It is often used for the same purpose that it is in railroading to prevent things from crashing together when they shouldn't. But more often it's used for one task to signal to another something has happened. And we're going to talk about two different types of semaphores today. We're going to talk about binary semaphore and a counting semaphore. So let's talk first of all about a binary semaphore. So as implied by the name, a binary semaphore can have a value of either 0 or 1. A value of 0 means that it takes on the meaning of used or not ready. And a non-zero value has the meaning of either either free or available. So in the Texas Instruments kernel, there are 3 primary functions we're going to use to talk about binary semaphores, and in fact counting semaphores as well, but we're just going to talk about the binary piece first. Semaphore construct, which actually creates the semaphore. Semaphore pend, which causes the task to pend until the semaphore is non-zero. And forgive me because I do not recall if in our last lecture we talked about the term pend, but I will repeat what a pend is. When we pend a task, the operating system, basically the operating system puts that task in a pending state and does not continue to execute the code until whatever caused the task to go into that pended state has cleared. So when we do a semaphore pend, it's telling the operating system, hey, I want to stop here until somebody puts something in this semaphore. So a semaphore pend will pause the task until the semaphore is greater than or equal to 0, or is greater than 0. And it's going to decrement the semaphore value. So if we are in the free or ready state, we are non-zero, typically a 1. For a binary semaphore, it absolutely has a 1. So what happens is when we call semaphore pend, the value is decremented, so now the value is 0, and the operating system won't return control to the task until it's been until that value has been changed. Now it turns out that one of the things that you can do is that you can say, you know what, I'm bored, I want to move ahead. So think about the situation at a railroad crossing. Some of you have probably been there when a gate has gone down and is stuck. And so you sit there with the gate down, with your car stopped, and no train is coming. And no train is coming, and no train is coming. And after 5 or 10 minutes, you decide that you're going to risk, sometimes less than 5 or 10 minutes, you're going to risk crossing and then pull out around the gate. By the way, not something that I recommend that you do. We don't want to have any of you killed at a railroad crossing because Professor Willie told you it was okay to go around the gate when it doesn't go back up. But as far as semaphores in real-time operating systems are concerned, sometimes it is appropriate to say, hey, wait a minute, I'm only going to wait here for this semaphore to kick over for 10 seconds, 20 seconds, a minute, 300 milliseconds, some timeout. So when you do that, you can, when you want to do that, you can tell, when you call semaphore pend, tell the operating system, hey, I want to wait for a particular number of timer ticks. And if the semaphore doesn't get posted, go ahead and tell me to go ahead and restart anyway. Now, having said that, you can also tell it, you can also pass this flag called BIOS wait forever. And BIOS wait forever does exactly what you would expect it to. Your task is going to pause for that pend, and it will wait until that gets pended or somebody turns the electrons off of your processor. And in most cases, that's the way we're going to use semaphores, unless we have a good reason to say, hey, we're going to give up. Another way to use a semaphore is to do a BIOS no wait. So the BIOS no wait tells the operating system, hey, look, I don't really want to pause here regardless of the state of the semaphore, but let's pretend that I did, and you let me know if the semaphore was already set before I got here. But if it wasn't, don't wait. And if it was, then go ahead and assume that I'm going to be using it and mark it as not ready now. So no wait never pauses for the operating system. BIOS wait forever pauses forever. If you use BIOS no wait, or if you use a timeout, you always have to check the status of the semaphore, because you don't know if you really got the semaphore if you're now in possession of it. What you do know is that you made an operating system call. So there is an error return value from semaphore pin that you can check, and you will need to check it if you either don't wait or use a timeout. So the other end of this thing is semaphore post. And all semaphore post does is that it increments the value of the semaphore and then tells the operating system, hey, we just changed the value of this semaphore. You might want to check to see if anybody is waiting. So the TI kernel has some oddities. The default behavior when a semaphore is posted is that the pending task, any task that might be pending on that semaphore, are readied in the order in which they pended on the semaphore, not the priority of the pending task. So let's say that your semaphore is something that controls access to the serial printer, okay? Under this behavior, what happens is that regardless of how important the task is that needs to use that serial printer, the first task to ask for use of the serial printer is going to get the access to the serial printer. And that's generally not the behavior that we want. Now, TI wrote this way because it makes the operating system faster. It's much quicker for them to make a decision in the operating system, in the kernel, if you just base it on the order in which people posted that are actually pinned on a semaphore. It turns out that they can do that in a lot fewer instruction cycles, which cuts down on operating system latency. But what it results in is a potential priority inversion, where a lower priority task, in effect, gets a higher priority simply because it asked first for a resource. That's not good behavior, and it is not typical of kernels. And the only reason that I can think of that TI did it this way was so that when they show people what their performance specs are, that the latency for semaphores is going to look substantially better by doing it this way. Having said that, in general, you will not want your semaphores, when you use semaphores, to operate this way. Fortunately, TI does allow you to change it so that it can operate semaphores on a priority basis. And what you do is, when you do the semaphore create, there's a flag that you set, and instead of using the semaphore mode counting or semaphore mode binary, you add the underscore priority to those two constants, and that gives you same behavior for your semaphores. So let's take a look at an actual use of a semaphore. And so you see two functions there. One of the functions is A to D read, and one of the functions is A to D complete. The code that you see up above is where, in some other chunk of code, we are initializing the semaphore. So we use this function called semaphore construct, and we're passing it two things. Number one, we're passing it this A to D sem struct, and that's how we actually refer to the semaphore. That structure contains all of the variables associated with the semaphore. And this structure called semparams is very similar to the structure that you use to set up a task and set up the task control block. So you can kind of think of this not so much as a task control block, but as a semaphore control block, the SEM structure. And semparams is how we get all of the appropriate information into that. So, and you can see that after doing the semaphore construct, we do something else called semaphore handle, which gets an address of the semaphore so that we can, rather than having to pass the structure around, we're basically passing off a pointer to that structure that we call a semaphore handle. And that's used in all of the other functions to figure out which semaphore we're talking about. So if we look at the, this is an A to D read function, and basically what it's going to do is that it's going to pinned on a semaphore, and it's going to start an A to D conversion, then pinned again, and when it's finished pending, the A to D conversion is complete and it can read the A to D conversion register. Now, the reason that we do the semaphore pinned before we actually start the conversion is that we want to make sure that the semaphore is in an unused state by when we get ready to start the conversion, that it hasn't already been posted for some reason. It's a synchronization issue. But we do a no wait, and we don't actually look at the error return code, because in this particular case, we just want to make sure that the semaphore is not ready, in the not ready state, before we start the conversion. So we start the A to D conversion, and then we pinned on the semaphore again. So we're going to be waiting there until something happens. This other function down here, A to D complete IRQ, is an interrupt that gets triggered after the A to D conversion is complete. So we've set up the A to D conversion someplace so that when the A to D interrupt handler goes to this A to D incomplete IRQ, and we pinned on that. When that gets posted by A to D complete IRQ, we can then read the value and return the A to D value. So I spent some time, it's all well and good to talk about how this works, but I spent some time putting together a video that I think is going to help you guys understand a little bit better how semaphores interact with one another during a typical exchange. So I'm going to pause here. It looks like we've got one person who is dropping in and dropping out. Is there somebody who's having connectivity problems? Yes, sir. Mr. Costas?
I'm having connectivity issues.
Okay, well, the good news is we're going to have it recorded, or recorded, so that you can get back to it. Hang in there. We're getting ready to go through some fun stuff. Okay, so let's take a look at some functions that I've written. The first one I'm going to call make dots. And as you can see, this is a highly complex function. What it does is that it prints a dot on the serial port using printf, and then it sleeps for one timer tick. And then it prints a dot on the screen, or on the serial port, and it sleeps for one timer tick. So it's tick, 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 printing out dots. Then I have this other function that I'm calling print A to D. And here's what it does. It's a while loop, and what it's going to do is that it's going to read the A to D converter, and then it's going to print the value that it read out that same serial port that the printf ... is going on. So in effect, what you're going to see, if this were a real function, is that you would see ... and then you'd see a number that would be an A to D value, and then some more dots, and then the number that's the A to D value. Now we have this A to D read. We need to create that program. And so what this does, very similar to the example that I just gave you before, it's going to start a conversion, and then it's going to pend while the conversion is in process, and then it's going to return the values in the A to D's result register. And I assume that rather than having to call a function, that we just have a predefined address that called A to D result reg that we're getting the actual result on the A to D converter from. And then we have the A to D interrupt function. So when the A to D conversion is complete, it's going to post that semaphore. Now I'm going to have little boxes associated with my task to show what state they're in: running, pending, ready, or interrupted. So when we start off, we are in the make dots function. It's in the running state. Print A to D is in the ready state. So this guy is running, and this little red arrow is effectively my program counter. So he's at the while 1, and he executes, and he does the printf of a dot, and then he sleeps. Now when he sleeps, we go from make dots being active to the next task. Let's go back here. This task was ready, so it goes to the next ready task here, which is print A to D. And print A to D is now in this, he's in his while loop, and he's going to call this function A to D read. So we are now in the function A to D read. Task is still ready. We're going to execute this start conversion function, and then we are going to pend on the semaphore that we're using to communicate whether or not the A to D conversion is complete. Make dots is still pending. Now print A to D is pending. So what does the operating system do? The highest priority remaining task is the idle task. And by the way, these are in priority order. So make dots is my second lowest priority. Print A to D is a higher priority than that. A to D read's not really is going to share its priority with print A to D, and then the A to D IRQ is obviously a very high priority. So the next thing that happens while the idle task is running is that the timer expires. Remember, we were over here sleeping in this function. So when that timer expires, now what's going to happen is we're going to do make dots is now ready to run. And so make dots is going to resume where it was. Remember, it had stopped over here at this sleep. And so this is going to come back to the while. It's going to print a dot. And oh my goodness, before we got through printing the dot, we got notice from this from the hardware interrupt that we needed to execute the A to D interrupt. So now print A to D is pending. Actually, make dot should have the interrupted box over it. That's a mistake on my slide. So make dots is interrupted. This guy right here is hosting the semaphore. Returning from that interrupt, make dots is ready, okay? But the higher priority task is print A to D, which shares its priority, or is A to D the higher priority task is print A to D, which was right here at this semaphore pin. And so the operating system, instead of going back to who got the interrupt, which would be make dots, it's going to go back to this function where the semaphore pended. And so this is going to execute. It's going to return the value. It's going to, we've now returned that value. So this val gets assigned whatever it is that we put in over here. We're going to print that out, come back, run the loop. We're going to say, let's start another A to D conversion. Remember, make dots is ready to execute, but it hasn't actually done anything yet, other than somewhere it's paused somewhere during this printf. Now we call A to D read. We're back over here. We're going to start the conversion. Then we're going to pend. And because of the semaphore pin, now the operating system says, okay, we're putting print A to D in pending. Make dots is now ready again, and it's going to finish up the printf statement. And then, of course, it'll do the task sleep, and all of this will repeat over and over and over again. So I'm hoping that that shows you a little bit about it. And you may want to review this section of the video a couple of times, because this kind of shows you how all of this stuff can interact in what's a relatively simple set of statements. You get some relatively complex behavior. One of the other things that we can use semaphores for is for locking a resource. So what you've seen is that semaphore was a flag that we've completed an event. We can also use it to lock a resource. And here's some examples of, the declarations. This is a more detailed example of how to initialize the thing. You'll notice that I have, during the initialization, we do the init, much like we did with creating a task control block. And we're taking in that initialized semaphore, we're setting its mode to be a binary priority-based semaphore. And we're going to construct the semaphore. And in this particular case, this is going to lock the availability for a UART. So the way we're going to use this is that in the function UART puts, we're going to pend on the semaphore that we just created. When the semaphore becomes available, then we will start printing out whatever it is that we're going to print. And when we're done doing our print for this particular string, we're going to post back to the handle. What's interesting about this particular example is that the post and the pend are actually in the same function. So if I have two different tasks calling UART puts, when the first task calls UART puts, it's going to, because we've set up this resource so that it's available initially, it's not going to pause here, but it's actually going to decrement that semaphore to 0. And it's going to wait. Oh, by the way, I missed that in the construct explaining that. This parameter right here, this 1, let me highlight him. Hello. That guy right there. That sets the initial value for the semaphore. And as you recall from earlier in the slides, that 1 indicates that the resource is available as opposed to unavailable. So that's that. So what's going to happen is that when the second function second task calls UART puts, if the first task is still busily putting stuff out to the serial port, the second function calling UART puts is going to hit this semaphore pin, and it's going to wait until the first guy to call UART puts gets down here and actually posts the semaphore as complete. So what that allows is that every time I do a UART puts, if I have my UART puts work this way, it makes sure that the entire string that I pass to it gets printed out before another task can write something else out to that port. Counting semaphores are something that you're not going to use very often. I will be quite frank with you that this example is kind of a stretch. The fact is that you're generally not going to use a counting semaphore this way, but there are very few examples where counting semaphore is appropriate in embedded applications. But let's talk a little bit about it, because the difference between a binary and a counting semaphore is that every time that you post, instead of just posting as a single ready, it actually will continue to increment the counter that's associated with the semaphore. So in this particular case, what happens is that every time I get a UART receive interrupt, I'm going to post to this RX semaphore value. Now, in this particular case, I've assumed that we have a serial port that has a FIFO buffer associated with it in hardware that can hold multiple characters. So every time we get a new character, we get an interrupt, and we're going to post to this semaphore, and it's going to increment it. So what happens is that the semaphore variable, in effect, indicates how many characters are available in the FIFO buffer. So what we're going to do on this read command is that it's going to go over here, and if there's nothing in the FIFO buffer, then that semaphore is going to be a 0. And when we do this semaphore pin, it's just going to pause for the operating system. As things happen and characters get posted into, or as characters get received in the FIFO buffer, each character that comes in is going to post. And so what's going to happen is that as soon as the first character is posted, we're going to break out of this, we're going to decrement the count, and we're going to get, we're going to put something from the FIFO into that buffer. And so you can see how if, for instance, before we got a chance to get care FIFO, if we had 4 or 5 different posts, this while loop would keep going until we've taken all of the available characters out of the FIFO buffer. So we're going to talk a little bit about what are the important calls that you need to be aware of in the TI kernel. So the first is this params init, which initializes the structure that's utilized to actually construct the semaphore. And you just pass it a pointer to a structure that you've created. Now, one of the much like with the operating system, this param structure, you only have to have one in your entire program, and it does not have to exist after you've finished creating all the different semaphores that you're going to be using. So this is basically pointing to a structure that we're going to throw away at a later date, but is used to pass information off to the semaphore construction function. The semaphore construction function requires a pointer to a structure that is permanent, and that is the structure that actually contains all of the information associated with the semaphore for all time. Count, right here, this parameter, is the initial value for the semaphore after creation. General rule of thumb, if the semaphore is going in a binary semaphore, if you're going to be using it to determine whether or not an event has occurred, you're generally going to start it off with a count of 0. And if you're going to use the semaphore to indicate for locking a resource, you're generally going to set it to 1. That being, if we're using this to indicate that something has happened, it hasn't happened yet when we create the semaphore, and so a 0 is the appropriate count for that. But if we're trying to talk about the resource, of the availability of a particular resource, 1 is a more appropriate value because, hey, we haven't done anything yet, so the resource is almost certainly available. And then, of course, you pass it the params that are over here. Semaphore handle just returns the handle that is used to for pinned and post to address the semaphore. Semaphore pinned is the function that that you use to pin. The handle is the semaphore that we're talking about, and you either pass it a timeout, which is going to be the number of ticks to wait before you give up on waiting for the semaphore, or you're going to pass it BIOS wait forever, which means that you're just going to wait there until the end of time or until the semaphore post. Or you can also do a BIOS no wait, which says we're not going to wait, but then I have to read this value, the semaphore pin value. I have to know whether it returned true or false. Obviously, if it returns false, that means that the semaphore timed out, or the semaphore hadn't been posted. And then finally, semaphore post, and in this case, we just give it a handle. So the last thing I want to talk about today are deadlocks. So a deadlock is exactly what it sounds like. It's where 2 tasks get to talking to the same resource, and something happens that causes them to crash and burn, and neither one ever execute again. This is very frustrating because when you're debugging, it's tough to know why a task is not executing, but the symptom of this is basically my code is executing and all of a sudden I've got 2 tasks that aren't doing anything and I don't know why. So here's how this scenario happens. So I've got 2 tasks, task A and task B. So task A is running along and it decides that it needs to pin on semaphore A. Right here, it pins on semaphore A. Well, semaphore A is available, so there's no pause. So task A simply is decrementing semaphore A to a 0, and he goes on about his merry way. Well, task B, which is a higher priority, all of a sudden decides, hey, I'm ready to run. Something has happened in task B. He's now ready to run. And so the operating system takes over from task A and passes control to task B. So task B now pins on semaphore B. Well, semaphore B happens to be available, so no problem. Semaphore B is now a 0, but task B continues to run because semaphore B was available at the time. The next thing that happens is that task B decides that he wants to pin on semaphore A. Well, he can't pin on semaphore, he can pin on semaphore A, but semaphore A is not available. It's a 0 because task A back here pinned it on semaphore A. So task B pauses. Well, the operating system says, well, my next task that's available is task A, so he resumes task A. Task A goes along doing whatever he's going to do, and then it decides that it needs to pin on semaphore B as well. Well, task B has semaphore B, and so semaphore B is a 0. So since semaphore B is not available, task A has to pause until semaphore B becomes available, which the operating system says, great, we're going to let everybody else run until either semaphore B becomes available, in which case I'd start running task A, or semaphore A becomes available, in which case I'd start running task B. Task A can't start because he's waiting on Task B to finish with Semaphore B. Task B can't start because he's waiting on Semaphore A, which can't be freed up because Task A can't do his thing. So what you've got now is that everybody's pending on something, nobody can move forward. That is called a deadlock. And it happens all the time, and it's generally because you haven't fully thought out how you're architecting your inter-task communications. So there are two ways to prevent deadlock. One is don't overuse semaphores, and in particular, avoid using multiple semaphores for tightly coupled resources. So, you know, in effect, if there's no semaphore B, you can't have a deadlock. An example of that might be an asynchronous serial port to have both a receive and a transmit resource. It's possible that if you're locking them separately, you could set up a scenario where there would be an issue. It's much better to have, in that case, a single semaphore that allows access to the serial port. The other thing happens, though, is that if you have multiple semaphores that really are required to make functions work, what you need to do is you need to document very clearly that what order they need to be pinned on. And as long as you always pinned in the same order, you never get out of trouble, get into trouble. So let's go back to this example here. So I've got task A. If you look at him without looking at task B, basically task A says, I'm going to pin on semaphore A, and then I'm going to pin on semaphore B. Okay, A, then B. Task B says, I'm going to pin on semaphore B, then I'm going to pin on semaphore A. That's where the lock came. If semaphore B had pinned on semaphore A before B, like A and B here, then what would have happened is task B would have pinned on semaphore A here. Task A would have resumed. It would have pinned on semaphore B, which would be available because task B hadn't stolen it from us. That old, bad old task B. And then we'd be able to, we'd be able to post in task A both semaphore B and semaphore A. Now semaphore B resumes and we're off to the races. So just making sure, if you have to have that situation, just making sure that everybody always pins and posts in the same order can prevent you from getting into that deadlock situation. So that's all I've got for this morning. Are there any questions? Any questions about the homework assignment? No. Homework assignment 2 is only timers. Excuse me, I don't know if everybody can see the chat. Mr. Prosic, we'll work on how to pronounce your name on Wednesday, has asked if we're going to be using semaphores in the homework assignment 2, and the answer is no. Also, don't forget to do your quiz on vocabulary on the first couple of lectures. Need that in this week. Any other questions? Awesome. Well, I will see you guys and gals bright and early on Wednesday morning. Y'all have a great day.